Hello everyone, welcome to the 7th MultiScale talk given by Dr. Anas Al-Azawi. Anas is a postdoctoral researcher at Aalto University in Finland. He has obtained his PhD degree in applied physics at the same institution. Today, Dr. Al-Azawi is going to talk about programmable and responsive superhydrophobic surfaces. So Anas, the screen is yours.
Thank you for your introduction, Zoran. Let me share my screen.
Yep.
Do you see?
Yeah.
Welcome to my talk entitled Programmable and Responsive Superhydrophobic Surfaces. Superhydrophobicity refers to the enhanced water repellency on surfaces. Water droplets roll off easily, collecting any dirt and contaminants in their path. There is huge potential of designing and implementing superhydrophobic surfaces because that will help in solving industrial scale problems. Solar cells can benefit from the self-cleaning properties imparted by applying superhydrophobic coatings. Dirt and contaminants can be easily removed from the surfaces, thus maintaining the high efficiency of solar cells. And in another example, superhydrophobic surfaces can be designed to combat icing. Water droplets can be repelled before they start to nucleate and form ice. In addition, superhydrophobic surfaces can be used to prevent the formation of the colonization of a wide variety of marine organisms. The biofouling that can cause increased drag of marine vessel and thus led to deficiency in fuel consumption. So in this talk, we will start by reviewing natural superhydrophobic surfaces as a motivation. And then we will have a brief theoretical background before we mention the characterization techniques that I have used in my work to characterize the superhydrophobic surfaces. And at the end, we will introduce bio-inspired cilia-like responsive superhydrophobic surfaces. The first example of a natural superhydrophobic surface is the wings of the cicada insects. These wings exhibit self-cleaning properties because of the roughness that is present on the wing, on the wings of these cicada insects. We have purchased such an insect, and we characterize the wettability of these wings by depositing water droplets on them. And this water droplet beat up nicely with high contact angle that can be easily removed by just slightly tilting the surface. We could visually inspect the nano roughness using scanning electron microscopy. And actually, this is not the actual surface of these wings, but it is a replica, polymeric replica obtained from these wings. And I will demonstrate to you how that the non-wettability can be seen. And it is by, we can attach water droplet to a needle and direct it into the surface. And we can see that the water droplet always stay connected to the needle and will not pin onto the surface of these cicada wings. Another example, it is of natural super hydrophobic or non-wettable surface is the surface of rose petal. We are familiar with rose petal. Droplets can bead up nicely on the surfaces. And that is due to the macroscopic structure of that present on the surface, consists of microstructures and also nanofolds on these microstructures. We have also like dried these rose petals and then characterized them. So this is image of these macrostructure after drying, and we can see this nanofolds. These nanofolds can pin the water droplets, and it is like the surface of the rose petal evolved such feature to capture the moisture from the air. And we can see that by repeating the same experiment that in this case, the water adhere to the surface, and in one of the location, the droplet will get pinned on the surface of the rose petal. So depositing any water droplets on any surface, the profile of the water droplet is dictated by the minimization of the free energy of the wetting system. The wettability of the wettability can be identified by measuring the contact angle, which is the angle between solid-liquid interfaces and the tangent to liquid air interfaces at the contact line where the three immiscible faces meet. According to the Young equation given here, the contact angle is given by the balance of the three interfacial free energies acting on the contact line. In fact, only on smooth, non-reactive, atomically flat, homogeneous surface that the contact angle is given by Young equation. And the contact angle given by Young equation, also known as the Young contact angle. But real surfaces exhibit chemical heterogeneity and surface roughness that can pin the droplet. So on real surfaces, the droplet can acquire multiple contact angles in a range limited by the receding contact angle, that is the minimum of the contact angle that we can measure, and the advancing contact angle, the highest contact angle that can we obtain on a real surface. In contrast to an ideal surface where only one contact angle at the thermodynamic equilibrium, which is the Young angle, can be obtained. But the reality, the surface, real surfaces, you can get several contact angles, and each time you deposit a droplet, the contact angle will be between the advancing and receding contact angle. So it's important to identify these, both advancing and receding contact angle, because that will give us the contact angle hysteresis, which is the difference between the advancing contact angle and the receding contact angle. And for superhydrophobic surfaces, the contact angle hysteresis is less than 10 degrees. And it is important to measure the range of the contact angle hysteresis, because that will help us evaluate the contact angle hysteresis force given by the Formage equation. So the contact angle hysteresis force is proportional to the hysteresis and also to the surface tension and the radius of the patch of the droplet mixed with the surface. So the lower the contact angle hysteresis force, the easier is to remove the droplet and manipulate the droplets. And this is essential in the successful application of superhydrophobic surfaces. So we have now established that roughness is important in characterizing and in finding the contact angle. So the contact angle on surfaces can have, like the droplet on surfaces can acquire one of two wetting modes. The first wetting mode refers to a mode where the water droplet is impelled into the surface features, such as that the rose petal, droplet on rose petal. Liquid is impelled into the between the macrostructure on the surfaces. That's why the droplet is highly adhesive in this case. And the apparent contact angle of such a droplet is given by the roughness ratio and the cosine to the contact angle on the equilibrium contact angle on smooth solid surface, or ion contact angle. And the roughness ratio is defined as the real surface area multiplied by the project area, which has value, always the value is larger than unity. The other wetting mode is the Cassie-Baxter mode. And in this wetting mode, the droplet only wets the top asperities of the structures. So it is resting on a composite solid and air interface. And the solid and the liquid forms a distinct contact angle with each component. So the apparent contact angle is weighted average of the solid liquid interface and liquid air interface. And it is given by the Cassie-Baxter equation. And the solid diffraction is the fraction of the surface that is in contact with the water droplet, and it can easily be deduced for as is shown here. So here we show that the solid diffraction is considering this unit cell area. It is just the area that is that's in contact. I mean, the area of the pillars contacting to the water droplet divided by the unit cell area. So I will show you in this figure how we measure the contact angles. So it is important, as we mentioned before, that we measure the advancing and receding contact angle in order to have the hysteresis value of our surface. So in this, the first example, it shows the measurement of the advancing contact angle. So we begin by depositing small droplet and then gradually increase the volume of droplet by adding more liquid. And then the value of the contact angle increase until it's saturated with the advancing contact angle. And this is the results shown on like a flat on planar silicon surface coated with hydrophobic material. On the other hand, the contact angle on the measurement of the receding contact angle is done by depositing large droplets, and we withdraw liquid gradually. So the contact, the volume of the droplet decreases with time until we reach the point where the contact lines start to recede. And as the contact lines start to recede, become unstable, and it is shown in this region. So here we can see that it is like around 90.8 degrees, the value of the value of the receding contact angle. So we manufactured using microfabrication technique by like define the pattern using photolithography and followed by silicon etch. We manufactured different macropillar surfaces, each with distinct value of solid liquid diffraction. And we measured the contact angles on these surfaces. We measured actually on 4 surfaces, and the 3.14 surfaces, we don't have the image included. I will mention why is that. But we can see the result of advancing and receding contact angle on these surfaces. And we see as the solid diffraction decreases, the contact angle hysteresis decreases also. But there is a problem with this table, with these results, because we cannot distinguish clearly between two surfaces with minor difference in solid liquid diffraction. For example, the surface with 1.6% solid diffraction and the surface with has similar contact angle hysteresis with the surface with 1.23% solid diffraction. And that is not acceptable because we need to have accurate interpretation of superhydrophobicity as we change the solid liquid diffraction or we change any other parameter that can affect the non-mutability. And here comes the force-based method, which provide an alternative and more precise way to characterize the non-mutability of surface. So the first force-based method that I will delve into is the oscillating droplet tribometer. So in this technique, we deposit water-based ferrofluid on the superhydrophobic surface that we need to characterize. And keep in mind that water-based ferrofluid has physical parameters such as density and surface tension, similar to that of water. There is small deviation. But the wettability, so the wettability can reflect that of a pure water. So we deposit, after depositing the droplet on the superhydrophobic surface, we bring it closer to a permanent magnet. And then we move the magnet in a transverse direction. So we bring the droplet in free decay oscillation, and these oscillations are damped by dissipative forces, which are contact angle hysteresis force that indicates friction and viscous dissipation. And this is a sketch show you the experiment. So we just move the magnet from location A to location B, and that will generate magnetic field gradient and increase the magnetic potential energy, which will bring the droplet into free decay oscillation that are damped by the dissipative forces. And this is a sketch of the magnetic of the harmonic potential will within which a droplet oscillation occur. So how the experiments are done using the oscillating droplet tribometer? Of course, we try we track the droplet position with time, and for each subsequent experiment, we increase the normal force by bringing the superhydrophobic surface closer to the permanent magnet. By this way, we can test the robustness of the calcivaxar state. So eventually, the droplet will collapse to the Wenzel state, to the highly adhesive state, and become immobile as we increase the normal force. So we so we use the same surfaces that we used to that I show you, and where we measured the contact angle using conventional contact angle continuity techniques. But this time we use the same surfaces to apply the same surfaces using the oscillating droplet tribometer. So we captured the oscillation profiles of each of these surfaces, and we fit the acquired droplet position with time with the solution of general harmonic oscillator. And by this way, we can extract the dissipative forces such as contact angle hysteresis force and viscous damping coefficient. So the extracted dissipative forces are plotted here against the contact line length on contact area. It is we plot the contact angle hysteresis force against the contact line length of the droplet and viscous dissipation against the contact area of the droplet. It's actually the fraction of it's only the values shown in the x-axis is the fraction of the contact line length and the fraction of the contact area that's in contact with the droplet. So we can see here that we can distinguish the friction forces for each surface clearly. And that evident how precise the oscillating droplet tribometer is for relating the non-wattability to the solid liquid fraction. Similarly, we can relate the dissipative forces to the type of the coating applied. So in this experiment, we have employed droplet oscillation on different surfaces that have the same solid liquid diffraction, but each surface was coated with a different chemical. And we can clearly see that we can get distinction of contact angle hysteresis forces for each chemical. One of the main advantages of droplet oscillation is that we can relate the impairment pressure, which is the pressure needed to induce quasi-Twinzel transition for a droplet in motion to the solid liquid fraction of that given surface. It is important to conduct such experiments because by this way we can test the robustness of the Cassi Baxter state for droplet in motion. We found out that a ferrofluid droplet in motion undergoes transition at lower pressure compared to a static droplet, as shown in this figure, where both critical pressure values are compared with the analytical calculated values. And in this figure, we show different region categorized according to the effect of pressure and solid liquid diffraction on the wetting in transition and friction. And this figure gives us indication of the limitation of each surface that we use in this study. Surfaces with high solid diffraction, they are more resistant against Cassi-Twinzel transition, but they can exhibit high friction. So now we move to the second part of the talk, where we talk of responsive superhydrophobic surfaces. And as a motivation, in a previous example, I showed that the silicon superhydrophobic surface based on silicon micropillars, which are static structures, but there is a lot of application that can benefit by designing a responsive superhydrophobic surfaces. One of the field it is within soft robotics, another with sensing, where you have flexible magnetic micropillars on magnetic sensing elements. So if you touch the surface, it will generate electric signal. And also this example can be used to measure the fluid flow in microfluidic devices. Another example is the measurement of blood coagulation. So in this example, like you have an array of magnetic micropillars, and you have deposit a droplet of blood on top of these pillars, and you measure the deflection angle by applying a given magnetic field. And of course, as the time goes, you have to increase the magnetic field to get the same deflection, because the blood coagulates with time, and that's how you can characterize blood coagulation. So we have use magnetic pillars to make like responsive superhydrophobic surfaces, because that we can manipulate the structure using magnetic field, and it is a non-invasive way to achieve manipulation. So in the first example, I will show you the fabrication of the array of PDMS magnetic pillars. And you can see that the fabrication process in detail in this by reading this paper, but it is just based on defining the pattern, the template using photolithography and silicon etch, and then we obtain PDMS replica and make a mixture of PDMS with the magnetic powder, in this case carbon iron powder, and then we immerse this assembly into liquid nitrogen, and that will cause a cleavage at the interface. And we can again apply a substrate layer of pure PDMS and peel that layer to get an array of magnetic pillars. And the advantage of this fabrication process that it can give you a substrate where you don't need to manually remove the excess particles. So you can just achieve so the magnetic material is only confined with the holes, as it's shown in this image of the substrate that achieved after cryogenic separation. This is a SEM image of of one of the samples that we produce, and in this example we show you just an image of low aspect ratio structure. We done the magnetic actuation of such a magnetic array by immersing the magnetic array into the sample of the magnetic array into different liquids, including isopropyl and silicone oil. And we can see we have two different aspect ratio, and we can see how the bending as we move the magnets. For the low aspect ratio pillar, the bending is limited in silicone oil, because the oil will penetrate into the structure, and that will change the mechanical properties. And we can use such an array to induce directional droplet motion by repetitive bending and recovery of this magnetic PDMS magnetic pillars. And keep in mind that in this example, we didn't use any technique to lower the hysteresis. So the droplet was moved solely by the mechanism of the bending, the repetitive mechanism of bending and recovery, as shown in this sketch. But the problem with this PDMS magnetic pillar is that it's only can function while they are immersed, because they have high aspect ratio. And I mean, only pillars with high aspect ratio can be used to induce droplet motion. And by removing like the sample from the liquid, the surface tension will ensure that the pillars collapse on each other, and we cannot use them in like in ambient condition. But you can, of course, use the surface again, insert it in isopropyl to silication, and that will recover the pillars in their initial state. So, and so now we move to another example. Here it's come like important because in this we use a different type of a polymer to make these flexible magnetic pillars. So we use toluene made of two components, one with 3 tile groups and the other with 2 allyl groups. And we can mix these two components together. And above UV exposure, the tile groups will be added to the allyl groups, and the cross-linking will ensure that the polymerization will happen across the entire surface. So here again, we just like make a PDMS master, and we deposit like a mixture of this toluene mixed with the particles, and we use permanent magnet to drive the magnetic particles into the holes. And after curing, we can separate the toluene magnetic pillars from the PDMS master, and we can use them for surface actuation. And here SEM images of the aspect ratio pillars, and this optical image shows the distribution of the particles within these the pillars. And we can immerse this pillars in liquid medium, because they also like collapse if we don't like apply critical point drying. So the surface tension will, after you immerse them, the surface and take them into the ambient media, the surface tension force will make sure that the pillars will be collapsed. So we done the actuation in isopropanol as shown here. So we can actuate them, and this is a side view perspective showing the deflection of the pillar upon the application of the magnetic field from a bar magnet. And we can, of course, make them like bending to so they can touch the base of the surface. The advantage of using toluene as a material for making the magnetic micropillars is that it is the ability to tune the mechanical as well as the surface properties. We can tune the mechanical property by changing the stoichiometric ratio or by increasing the cross-linking density of the toluene polymer. We have like, and we have used electromagnetic needle to measure the deflection of different toluene magnetic micropillars. But in the first example, we have one type, the similar micropillar, but it was subjected to different to increasing magnetic to field by passing higher current through the needle. And we can see that the higher the current, the larger deflection of the needle. But by changing the mechanical properties, so here we have 3 different types of pillars. this is the higher cross-linking density is this is the stoichiometric pillars that's similar to that one, and this is the off-stoichiometric that so there is 50% excess tile in the composition, and by applying the same current through the needle, so we can get different deflection value, and that reflects the change in the mechanical properties. We can easily see how the how the deflection varies across these different samples. There's less here because this sample is stiffer because the higher cross-linking density, but and it is here. The deflection is highest because because it is off-stoichiometric, so there is an excess of tile will make the polymer material slightly more flexible. And we in this figure we have compiled of all of the characterization, and you see how how the deflection changes by increasing the supplied current to the needle, and also by the changing the initial pillar needle distance. And these are snapshot images of the videos that I showed in the previous slide. Now we move that we have now mentioned the how we can tune the mechanical properties of the pillars. The other advantage of using tile-in macro pillars is that we can also tune the surface properties, because on the surface of the tile pillar there are functional groups, the tile groups and allele groups, and we can use this group to covalently bond colloids onto the surface. So in these SEM images show you that we use polyphenol trimethylhydroxysilane colloidal macro and nanoparticles. So these are silica particles in the core, but they have allele termination, so they can bind to the tile groups present on the surface of these magnetic macropillars. And upon such surface activation, we can get dual surface roughness. So we can treat these colloids with the hydrophobic self-assembled monolayer. So the result is superhydrophobic and flexible magnetic pillars. And this also gives the surface advantages. So they make the pillars resistant to collapse. So we showed here SEM characterization after the application of these colloids. And we didn't need to do a critical point drying. So it is just this surface can function in liquid media and also can function in air as well. And yeah, this is just the same pillars, but in this example, it's just coated with the beads or with the size equal to 450 nanometers. And we can use such surfaces to induce directional droplet motion, as shown in this video. So once again, there is the motion was facilitated only by the action of repetitive bending and recovery of these pillars. So the hysteresis was so low, so we didn't induce any other means to combat the effect of contact angle hysteresis, because the dual scale roughness has reduced the contact angle hysteresis to such value that we can manipulate water droplets just by manually manipulating the magnet beneath the sample. In conclusion, we have showed you how to accurately characterize superhydrophobic surfaces by employing droplet oscillation, and we can prove the variation in both pattern density and also chemical coating by just performing ferrofluid droplet oscillation on superhydrophobic surfaces. And you have seen how we can make responsive superhydrophobic surface that can be used to manipulate water droplets, and such surface has several applications within the medical field and within the microfluidic systems. We show you two types of like magnetic pillars based on two different materials. One is PDMS, and the other is the tunable toluene material. And that will conclude my talk. Thank you for listening. And now I am happy to receive any questions.
Great. Thanks for the beautiful presentation. I'm actually glad that I have been participating in the latest work that was presented here. So
yes.
Yeah, that was very good.
Yeah, so the actuation of this toluene part micropillar was done in collaboration with you. Yeah. And we have it was very nice to see how that the deflection of these toluene pillars, how can we see it using the electromagnetic needle, and that's helped us to relate the mechanical properties of these pillars to the deflection and flexibility.
Yes, true that. Yes, it was very good work. I really like that one. Just now, one question: when you were moving the droplets and the beads, did you ever try with a rod? Probably, because beads and drops, they have both spherical shape. But can this concept work with, I don't know, a rod?
A rod, yes. I cannot see why it cannot work. I mean, it was much easier to move the beads because they are solid objects, but with droplets, you have contact angle hysteresis, and you have to overcome that. So yes, of course, a rod can be moved, but I don't know if we can achieve directional motion of the rod, because it can change the orientation.
Yes.
And yes, you can use such surfaces to manipulate the rods, but keep in mind that the size of the rods has to be higher than the pitch value of this array. So it cannot be fall between and get stuck in the array.
True that. Yeah. So regarding this Tribometer, so you're using a Tribometer to characterize the superhydrophobic surface, correct?
Yes. Yes.
So there is also this contact angle as you showed measurements. So
yes.
goniometer, and then there is also another technique coming again from your group, this scanning, SDAM scanning, droplet adhesion microscopy.
Yes.
So now a bit stupid question: which one is the best?
There is no a better technique than other. These techniques complement each other. For example, the contact angle goniometer is very good to measure hydrophobic, hydrophilic contact angles and weakly superhydrophobic surfaces. But as you get as your surface is superhydrophobic, it will get more difficult to do a measurement because your droplet will stick into the needle and it's difficult to deposit on the surface. And then it will be difficult to position the baseline, and because it is the technique based on acquiring the shape of the droplet, and the fitting mechanism will give you the contact angle. So I mean, it's the contact angle goniometry is good, but it's not great for when characterizing superhydrophobic surfaces. And for oscillating droplet tribometer, it has also its limitation. It is only limited to planar surface, and we cannot. You have to have enough area to perform the oscillation. So the surfaces that I showed, that they have the length of the structure fields around, as average, around 8 centimeters. So you cannot characterize like a short, like small fields. The contact scanning droplet adhesion microscopy is that when you have a droplet in contact with a force sensor, and as it touches the surface, you can measure the pinning of the droplet and the force needed to de-wet the droplet from the surface. This is good to measure the like surfaces, small areas on surfaces, and also non-planar surfaces. So if you have non-planar surfaces and small areas, it's better to go to the scanning droplet adhesion microscopy. If you have large area, you can do droplet oscillating droplet tribometer, because that is easier to measure. Yeah.
Yeah. So, you know, like there are many companies selling this, the goniometer. So are there companies selling this, or if someone wants to characterize a surface with a tribometer, can they just buy a device for that, or they just need to build their own experimental setup and characterize it?
At the moment, there is no device that you can purchase. You can either make your own setup, or you can contact a group that have this setup ready, and ask them to characterize your surface. So far, it is only the contact angle goniometry that is available, and it is the most widely used technique in characterizing the surface non-wettability or wettability.
Yep. Well, with that, I'm going to conclude today's MultiScale talk. Thank you again for the very, very detailed talk and very detailed answers to all my questions. And I hope that you'll be guest again. You can give a talk at some point in the future when some new results from your research will come out.
Thank you, Zoran. Thank you for having me, and I am looking forward to give another talk in the future.
Great. Bye-bye.
Goodbye.